Hello and welcome. In this supplementary video, we're going to be helping you fill in our reading notes for fluid statics. Now, if you've been digging into the Etkina college physics online textbook that we have, you should have been able to fill out a good majority of the notes as we go. So this is more of a supplementary resource to help you fill in anything that is necessary to finish. Let's begin. Section 10.1, density. State the basic equation for density. Define the symbols. Well, the equation for density is rho equals mass divided by volume, where density is the variable rho, the Greek letter rho, and its units are kilograms per cubic meter. M is in mass, that's in kilograms. V is volume, which is going to be in cubic meters. Briefly explain how to measure density of an irregularly shaped object where the volume cannot be determined by using a geometric formula. First, find its mass using a scale. Then determine its volume by submerging it in a graduated cylinder or some measuring device, a beaker, I suppose, but a graduated cylinder is a little bit more precise. Finally, divide the mass in kilograms by the volume in cubic meters to find the density in kilograms per cubic meter. Explain how the density of an object determines whether it will float or sink in a fluid. Well, the simple old adage is less dense objects float on more dense objects. So the lighter the object, the less dense the object is, the more it will float on top of more dense objects. On a molecular level, why do denser fluids sink below less dense fluids? Well, denser fluids are heavier, which means they have more mass. Therefore, they're more dense and sink below less dense fluids. If an object is made of pieces of different substances, such as a person made of flesh and bone, both of which have different densities, then how can the average density be defined? What do you think about the equation for average density? Just think of it as total mass divided by total volume. Section 9.2, pressure, density, and the mass of particles. So in this particular one, you are asked to go back to Chapter 9, Section 2 in the Etkina College Physics textbook to kind of get a handle on randomly moving particles and how that defines the concept of pressure, which we can then apply to fluids. So how can randomly moving molecules cause pressure to be exerted on a surface? Well, the moving molecules make collisions with the walls of the container and collectively result in a force exerted over a certain area. And first, a force per unit area is defined as pressure. Name 2 ways to inflate a balloon. One of them is the obvious old-fashioned way. Well, the obvious old-fashioned way, of course, is to blow air into it. Add moles of gas to the balloon, you'll increase the volume of the balloon. But the other way would be to decrease the pressure on the outside of the balloon. So, for instance, if you take this sealed balloon and you put it in a vacuum chamber by definition is a region of no air. You suck the air out of it, right? So the pressure outside of the balloon will be less due to the air being less air. So the pressure on the inside of the balloon being greater causes the air to kind of push outward and therefore expanding the balloon. What is the basic equation for pressure exerted on a surface? Explain all symbols. Again, pressure is force per unit area. Pressure is either measured in pascals or newtons per square meter. Force has been in newtons, still be in newtons. Area will be measured in square meters. Explain gauge pressure. The antonym of gauge pressure is absolute pressure. Clearly explain the difference between these two terms. Well, gauge pressure is the difference between the pressure in some container and the atmospheric pressure outside. So, for instance, when you measure the pressure in your tires and it measures out to be, let's say, 35 pounds per square inch, that is a difference between the atmospheric pressure outside and the pressure inside the actual tire. The absolute pressure is the total pressure or gauge pressure plus the atmospheric pressure. Section 10.3, pressure with varying depth. Why is the water's parabolic path wider at the bottom than at the top? Okay, this is from figure 10.7. And what you saw in that figure is you saw more or less something like this, and then a stream of water coming out of a hole made near the bottom. And if you think about it, pressure is going to be more, right, where the depth is greater. So if the depth is greater down here, there's greater pressure down there, and more pressure, right, is going to force the fluids out with greater speed near the bottom than at the top. Look at figure 10.8. The three black print sentences talk about the absolute pressure acting on books at different levels. Okay, what would the black print sentence say if the author considered gauge pressure? Okay, so if you're considering gauge pressure, that means you eliminate air pressure. So the author is saying only air pushes down. Well, gauge pressure eliminates air pressure, so there would be essentially no pressure pushing down on the first book. Okay, so for the first one was the first book. Now, the second one, the author was talking about, I think, the fifth book down, which would be, now they say the pressure coming from book one plus 4 books pushing down. So this would just be the pressure. The pressure on the fifth book would be the pressure from 4 books above, which would be essentially the weight of the books divided by the area that they're applying their weight on. Okay, and then same thing with the last one. The last one was that bottom book, the 10th book, would be essentially the pressure coming from the air above book 1 plus the 9 books. Well, again, we're not accounting for air pressure, so it's really just the pressure, whoops, sorry, I can't write today, pressure from 9 books above. So again, the difference in this second column here is that for gauge pressure, we're only accounting for the essentially the fluid pressure. The gauge pressure is only accounting for the fluid pressure. It's not accounting for the air pressure outside the container, or in this case, outside the stack of books. Okay, so a family drives from Colorado Springs to the summit of Pike Peaks. In the car, a sealed bag of chips gradually inflates as the car rises to the summit. Explain how this happens in terms of pressure at the base and top of the mountain. Use the book's discussion of a water bottle in an airplane to help. So as the car gets higher in elevation, the atmospheric pressure is going to decrease compared to the atmospheric pressure inside the sealed bag of chips. Since the pressure becomes greater inside the bag comparatively to the outside of the air will push against the bag and the bag will appear to inflate. State Pascal's second law, which gives the variation of pressure with depth in a fluid as an equation. Draw the diagram to give meaning to 1 and 2. So pressure 1 in a fluid is the position at Y1, and it can be determined from the pressure of 2, Y2, which is P1, which is the absolute or total pressure, is equal to P2. And you can see P2 is up here. That's the atmospheric pressure. P2 is the atmospheric pressure, plus the gauge pressure. So all of this, rho of the fluid times the difference in your positions, which is the depth, times G, that's your gauge pressure. Okay, where rho of the fluid is the density of the fluid, assumed to be constant throughout the fluid. Now, explain the trick that Blaise Pascal performed in order to test second law. So what he did is he had a big, long barrel. Okay, now the barrel was filled with water. And in the top of it, he stuck a long tube, okay, which was very skinny. It was a very, very skinny tube. And he filled the tube with more water. And he hypothesized that since pressure depends only on the height rather than the amount of fluid, that even a skinny amount of water added at a much greater height, and we're talking, upwards of like 10 meters, right? So at this height, it's just going to create so much pressure in the barrel that it's going to cause essentially so much pressure the barrel would burst. And that's exactly what happened. The barrel burst open. Explain Pascal's paradox. Draw a diagram to assist your explanation. Try to make your explanation shorter and simpler than the textbook's explanation. So he came up with a paradoxical situation that involved an apparatus that you see over to the right. Now, as you see over to the right, you have essentially differently shaped objects. Now, all the objects are open to the air, okay, from above, which means they're all open to atmospheric pressure. You can see the water level, right, is equal in each of these. But the geometry of the containers is significantly different. Well, what he found is no matter what the configuration or the shape of the container, as long as it was open to the atmosphere and contained the same atmospheric pressure, obviously pushing on it, it would be filled to the same water level, and thus the pressure at any height, or in this case depth, would always be the same. Section 10.4, Measuring Atmospheric Pressure. Explain how Evangelista Torricelli measured the pressure of the atmosphere. Use a diagram to assist in your explanation. Okay. I'm going to go ahead and uncover this one too, just so we can see. So what he used a suction pump, okay, basically a long syringe to lift the fluid. Now, on top of the syringe, you're creating a very low pressure environment, which means fluids always move from high pressure to low pressure. So the fluids would essentially be sucked up, right, or forced up towards the region of lower pressure, right, as the plunger is pushed up, or pulled up, rather. Now, what he found using this idea here, which was really interesting because he came up with this idea well before Pascal published his second law. This is essentially Pascal's second law, but he hadn't published it yet. So kind of amazing how Torricelli came out with this. Pascal actually published second law the year Torricelli died, in fact. But essentially, as you can see, we have P2 is the same as P1 because they're at the same level. And P3 is going to represent this pressure here. Okay, and so P3, the pressure there plus the pressure within the fluid, okay, would help us figure out the pressure down at level 2. And by multiplying that together, again, zero pressure here, rho times g times h gives you about 101 times 10 to the fifth pascals. State Pascal's first law. Well, Pascal's first law essentially is stating what this is right here. An increase in pressure of a fluid is static and closed at one place is going to be uniform throughout the fluid. So no matter what, I'm sorry, that's that second law. The pressure within a fluid is always going to be constant, and that's essentially what explains how hydraulics work. So let's explain how hydraulics work. We're going to have a little diagram here, sketch the diagram with your explanation to help with the explanation. So here's the diagram. We have a small downward force applied on a piston of fluid with a small cross-sectional area. Now, this amount of pressure that's applied on the fluid is constant throughout. So you're applying the same fluid, but you're applying the same fluid on an area of much bigger cross-sectional area, which will apply a much larger upward force, right? That's how you can get hydraulic lifts to lift large objects like cars, or forklifts to lift very large masses, things like that. Explain what happened in Pascal's syringe demonstration. How do your observations verify Pascal's principle? So this demonstration is an application of Pascal's first law. The syringe was connected to a glass hole. So let me kind of sketch it for you in case you hadn't seen it. So you've got this long syringe filled with fluid. Here's your plunger. Fluid's in here. Okay, so you're pressing on the fluid, and at the end of the fluid was a glass bulb. Now, this bulb had several holes in it. Now, as the fluid was pushed, it was noticed and observed that the fluid came out with equal speed and therefore equal pressure, meaning the fluid pressure is constant all throughout the fluid, which is Pascal's principle. Pascal's principle is Pascal's first law, in effect. Well, now in section 10.5, we're going to get into buoyant forces, okay? So you were supposed to read observational experiment 10.4, okay? And in this observational experiment, you essentially had an object that was weighed, and then it was dunked in a fluid, okay? So essentially what you have is you weigh an object on a spring, right? And you have the weight of the object, okay? But then you have the spring force, okay? And they're balanced, right? So that would help you essentially figure out, by measuring the spring scale here, you could figure out essentially the weight of the object almost directly. But now you take that same object and you put it in a fluid. Now it's still attached to the same spring constant, same mass. But this time, the spring does not stretch as far. So the spring scale reading will be less. The mg, or the weight, will be the same because it's the same mass, same acceleration to gravity, but because there is an upward force due to buoyancy, right? These two forces are now going to balance the weight. So it's the buoyant force that is making less spring force, right? Which means the spring will stretch less. That's exactly what was observed. So the spring stretches, the spring length will be shortened. This is because the fluid applies an upward buoyant force on the ball. This upward buoyant force reduces the force pulling by the spring, thus the spring length is shorter. Now, there is a small mistake on the arrows drawn in figure 10.3. In a single sentence, explain and the mistake, then draw the correction to the right. So here's the diagram over to the right. So basically, we know that here's how buoyancy works. Okay, you have a greater pressure from down below, because remember, pressure is greater at greater depth than you do from above. So that's why I'm drawing the pressure arrow longer above than below. Now, on the sides, the pressure should be balanced. Should be the same length on both sides. Now, the textbook makes the mistake because they draw it like this. They draw exactly the same length going all the way down. But we just got done saying pressure increases with depth. So this should be longer, but equal to this. And this should be longer, but equal to this, if that makes sense. So it's still balanced on both sides of the cube on either horizontal side or against each vertical face. But as you go down the side, the arrows should have been longer. Using a diagram that you just drew, explain how the fluid pressure causes buoyancy. Well, we just explained it, so let's articulate it in words. So pressure on the vertical sides always cancels because pressure at depth is the same at each level of depth. The pressure on the bottom of the mass is greater than at the top of the mass because pressure is greater at a greater depth. This greater pressure from under the mass results in a net upward force known as buoyancy. The equation for buoyancy is B is equal to rho of the fluid times V times G, where the buoyant force is in newtons, rho of the fluid is still in kilograms per cubic meter, volume is still in cubic meters. So let's just write an equation for the weight of an object using rho without using mass. So, and then compare the buoyant force in the equation. So the idea is if you solve for mass, so density is mass per unit volume, but if you solve for mass, mass is density times volume. So if weight of an object is mv or mg, mass of the fluid times g, or mass of an object times g, then it's, sorry, this is supposed to be mass of an object. Then it's the density of the object times volume of the object times g. So that's how you can write the weight as in terms of density rather than in terms of mass. Okay, so in section 10.6, skills for analyzing static fluid processes. So read example 10.6 and explain why we haven't considered buoyancy on the force of air acting on cars, blocks, and balls at any time before. So basically the question has a person standing on a scale. There's a person standing on a scale, and you have their scale reading because you've got the normal force and it balances the weight, but the normal force, that's really the scale reading pushing up under the person's feet, right? Well, the question essentially calculates, the figure in the example essentially calculates the fact that even if you account for the pressure due to the buoyancy of air, there's not a whole lot of difference. There's pretty much insignificant difference due to the buoyancy of air. And if you think about it, the density of air is just so low, right? The density of water is about 1,000. The density of air is about 1.2, right? So you're not going to get a whole lot of upward force. And remember, to get buoyancy, there has to be a difference in pressure. So there's not a whole lot of difference in pressure from the bottom of the person, right, pushing up, as opposed to the top of the person pushing down. There's just not much pressure difference to create buoyancy. Okay, what are the three cases regarding buoyancy? Well, case number one, if an object is less dense than the fluid, the object will float. If the object is the same density, then it's going to remain exactly where it is in that part of the fluid. Meaning it'll float, but it'll be exactly that spot. It won't rise, won't sink. If the object's greater density than that of the fluid, it's going to sink and accelerate to the bottom. So then how is this used to discuss why submarines can control their ability to float and sink. Well, if you think about it, a submarine is basically hundreds of thousands of tons of, steel and concrete and, you name it. It's a big chunk of metal, right? But it's filled with air. So the air makes it very buoyant compared to the heavy pressure water outside. But how can you get it to sink? Well, that's pretty simple. You add water. So it basically what you do is you fill compartments within the submarine with water. So if you fill it with water, then you make the submarine density greater than that of the outside. It's going to sink, right? But then when the water's pumped out, right, leaving the compartments empty, the submarine's density decreases. That allows the submarine to rise. The water is the only thing that can be changed, pumping the water in or out. So in this next example, it says the Titanic was made out of steel, which is about 7.75 times more dense than water. So it doesn't really make sense that something that much, almost 8 times greater than water, should sink in water, right? So a student, when presented with this information, states that the Titanic should have sunk the instant it was set to sea in Belfast. Using the terms of average density, explain why the Titanic can float. Well, the Titanic basically can float because it's filled with compartments with air. So it may be steel on the outside, right? But it was filled with compartments with air, which, as we've already mentioned, has significantly lower density than that of water. So if we take into the average density of the Titanic was actually less than the seawater around it because of many compartments filled with air. Which is also the same reason why ice floats. Not only the crystal structure of ice giving it a greater essential volume compared to its mass, but also it has little pockets and holes of air, and that allows to make it less dense and thus float on water. So once the Titanic hull was breached by the iceberg, the average density of the Titanic changed until its conditions were met for the Titanic to sink. Explain how the Titanic's average density changed. Well, if you think about it, if once the breach happened, the Titanic takes on water, the average density increases because those air compartments are now filled with water. So if the average density goes up compared to the water around, and the average density becomes greater than the water around, then what happens? You're going to sink. So density is 90%, the density of ice, is 90% of the density of seawater. For the iceberg to sink, that sank the Titanic, how much of the iceberg was visible above the water surface? What does this imply about the danger that the iceberg poses to a ship? So what we know is that the density of the mass of the fluid equals the mass of the fluid displaced equals the mass of the object that's displacing the fluid. That's Archimedes' principle. Now G cancels, you can see that. And we're left with rho of the fluid via the fluid equals rho of the object via the object. And if we solve for this ratio here, V of the fluid divided by V of the object gives you the percentage of the volume submerged. And the percentage of the volume submerged is this ratio of the densities, density of the object, density of the fluid. Well, the density of the object is, we were told right here, 90% of the density of seawater. So we can change density of the object into 0.90 density of the fluid. Those cancel. What does that tell you? 90% of the iceberg is below the surface, therefore only 10% is visible. Now, this section's not in the book, so let's talk about variable density fluids. Starting from the equation P equals P naught plus rho GH, perform a derivation to explain what the slope of pressure versus height of a graph represents. So if you look at the graph here, let's rewrite the equation as rho GH versus P naught, and you can see we are plotting pressure on the y-axis, you're plotting height, or rather depth, on the x-axis, you can see that the y-intercept is your atmospheric pressure, which tells you that the slope is rho times g, which means if you divide by the slope by g, you'll be able to figure out the density of the fluid. Now, in this example, it says the air pressure as a function of height above sea level is shown in the graph below. Using the graph, estimate the density of air at the height of Mount Everest, which is, it's about 8,800 meters. So we're just going to kind of round up to 9,000 meters, okay, as a height. So what I'm thinking is go to about 9,000 meters, which is right there. Okay, you can see that corresponds to that data point. And then if we go across, that seems to, I don't know, maybe about 3.7 roughly times 10 to times 10,000, which would be essentially a total pressure of 37,000 pascals. Okay, so using our equation, P equals P naught plus rho GH. What I'm thinking is, let's go ahead and subtract this over here, subtract P over here, and rearranging the equation, we get rho GH equals P naught plus P. And then you can divide away the GH, and that will help you solve for the density of the fluid. So the density of the fluid, rho, you got the atmospheric pressure, which is 101,300 pascals, minus what we just got here, 37,000. That's a 7, by the way, not a 2. 37,000 pascals, and divide that by G is 10. Height is, remember, it was about 9,000 meters. So what we're doing is taking 101,300, okay, in our calculator. Go ahead and subtract 37,000, and then divide by 90,000, and you will get a density of about 0.714 kilograms per cubic meter. Now, why does that make sense? Well, the density of air at sea level is about 1.29 kilograms per cubic meter. But the higher you go into the altitude, you have not only less and less air pushing on you, the air pressure is less because the molecules are more spread out, right? If the air is just going to be less dense, there's less mass of air up there, right, compared to that of sea level. So as you rise, not only is air pressure getting less, but air pressure is, the density of the air is also getting less too. Okay, now to finish this off, I'm going to let you do this one yourself. I'm going to give you a small hint, okay? But let's read this last part together. Suppose a tiny balloon is less dense than that of air is released from sea level. You know, maybe something filled with helium or something. The balloon is made out of a smooth and rigid space-age material so that the volume does not change as it rises, so it's not going to inflate, okay? And it encounters no air resistance as it rises. If the balloon is subject only to the forces of weight and buoyancy from the air, how will its acceleration and upward velocity change as it rises from sea level to 20,000 meters high? Okay, so please take a few moments to express your thoughts in a reasoned out paragraph. The main hint I'm going to give you is that the higher you go into the altitude, your density and your air pressure will be less. Well, I hope you found this to be helpful. Thank you. See you next time.